Good day. In this video, we will be showing our research project entitled Extracting Medication Information from Typewritten Philippine Medical Prescriptions using Optical Character Recognition, OCR, and Named Entity Recognition, NER. The problem this research tries to explore is that studies that both extract and parse prescriptions are limited to those that use Latin abbreviations and other formats for infrequency, which are not used in the Philippines. The general objective of the study is to develop a web application that extracts information from typewritten Philippine drug prescriptions. So there are 4 specific objectives that this study tries to tackle. So one is to create a dataset of typewritten drug prescriptions from the Philippines. Number 2 is to utilize an existing OCR tool, Tesseract, to transform Philippine prescription images to text. Number 3 is to utilize a natural language processing or NLP tool, SPACY, to extract medication information by annotating the resulting text from the OCR tool. Number 4 is to incorporate OCR and information extraction techniques for the automatic transformation of prescription images into textual medication information. So for the scope and limitations, the prescriptions that were used are in English and are from the Philippines. There were some samples from previous studies, some collected through Google Forms, and synthetic data generated using the collected samples. The information extracted are dosage, drug, duration, form, frequency, strength, tablets, when, how, and remarks. No sensitive data is included. This was implemented as a web application using Tesseract OCR and SPACY. So for our methodology, we have performed the following steps. We reviewed related literature, created a dataset, evaluated OCR tools, performed information extraction, and created a web application. To achieve those objectives, this study uses a dataset of Philippine medical prescriptions. 50 prescriptions were collected through Google Forms and personal collection. These prescriptions were then cropped and converted manually into 3 different formats for typewritten prescriptions. In addition to its own original format, resulting in a total of 166 data samples. The 3 typewritten prescription formats were gotten from the originally typewritten sample prescriptions collected. The 3 formats includes one that is numbered by drug name and has a sig line clearly labeled. Another has the drug name separated by only spaces and new lines and a shorthand way of writing the frequency. And the third line is similar to the second, but has a longhand way of writing the frequency. A sample from the dataset was used to create a set of images that simulated a user taking a picture of their prescriptions from different angles and lighting conditions with their mobile phones to test for skewness. This is represented as the skewed or distorted dataset. The dataset created was verified by 2 medical professionals.
You can see here the performance of Tesseract. When tested with the dataset, it had an accuracy of 4.7311% average character error rate and 12.4990% average word error rate. Here is a sample output from Tesseract where the highlighted one is the correct one. These are the pre-processing techniques we tested. The first technique will find hue lines in an image and get the most common angle of the lines to get the correct rotation. The next technique will try to test each possible rotation and get summation of the pixel values horizontally. The angle with the best score will be used to deskew the image. The next algorithm will look for 4 corners in the image and morph it into a rectangle. The last technique will be shadow removal, which uses blurring of the image to detect the background and normalize it. All these techniques involve grayscale conversion. As seen in the results, shadow removal has no effect since the dataset has no shadows. The better technique is using hue lines. Additionally, it is faster than histogram since it does not look through each rotation angles. Here we can see 2 closely comparable techniques which are hue lines and histogram both with shadow removal. Using binarization after these two techniques was not able to help. The post-processing uses regular expression to correct common mistakes done by the OCR. The use of post-processing gave a small boost in accuracy in the default dataset. The same can also be said in skewed dataset, except for the first row, which is a big boost in accuracy. Both hue lines with shadow removal and histogram with shadow removal are still close. However, hue lines with shadow removal is chosen since it is more accurate and it is significantly faster.
For information extraction, SPACY, an industrial-grade NLP tool with various features of NLP techniques, was used to create the information extraction model. This is the same tool used by Med7, an information extraction model for clinical text created for the I2B2 challenge in 2018. Two SPACY models were trained for this study, one with all the entities and another containing only the 4 new entities, namely number of units, when, how, and remarks. These are entities that are not part of the Med7 model. The two models that were trained were tested into 3 different configurations. One is Model 1, which is trained with the complete entities alone. The second is Model 1 on top of the Med7 model. And the last one is Model 2, which is trained with the new entities only on top of the Med7 model. Overall, the Model 1 had the highest F-score of 0.9316 and a 5-fold cross-validation score of 0.9793. The complete standalone model is the one used in the final web application. For an overall testing, we tested both the OCR and NER module in one go, and the results show fairly high accuracy with the F-score being 0.8816. With the distorted dataset, the overall F-score came out to be 0.9215.
The application also has a spelling suggestion. A list of medicine names was scraped from the MIMS website, which contains a list of drugs sold in the Philippines. The first library in Python was used to check the Levenshtein distance between the medicine name read by the OCR and the list of medicine names scraped from the website and suggests the medicine name from the list with the closest Levenshtein distance. The spelling suggestion was able to find 31.30% of medicine names in the dataset match with the list of medicine names scraped from the website. 47.25% of the incorrect medicine names were corrected, and 24.35% of the incorrect medicine names were not able to be corrected accurately.
After performing the tests on Tesseract and the NER models, we have created a web application prototype. Here is a short demo of the web application. So here on the screen is the image that we will be inputting into the website. So during the loading, the image will go through pre-processing into the OCR tool, post-processing, then into the NER module. So here is the result. So in the tooltip, we can see the spelling suggestion. And here we can see that the table can be edited. So when downloading, the output will be a CSV file, and it will be exactly the same as on the website, including the edits. So that is all for our presentation. Thank you for listening.